Hi there everyone, welcome to this video. Last time we covered till chapter 2 and touched upon very important measures like mean and median. And the first thing we are going to cover today is a continuation from chapter 2, another very important measure which is called standard deviation. Now, standard deviation very specifically measures the spread of data across the mean. Now, that's a very technical definition. Let's take an example. Say you went to a clinic to do a regular health checkup and you notice that your blood pressure is 10 units higher than an average person's blood pressure. Yours is 135 while the national average is 125. Should you be worried? Short answer, no. Because the standard deviation of blood pressure across the country is 10. That means 90% of people would have a systolic blood pressure ranging from 105 to 145. That is, you are amongst the normal. That is, you are not a rare case and this is an expected deviation while measuring blood pressure. However, if this was the case of measuring something else, let's say oxygen levels in blood, which typically has a standard deviation of 2 percentage units, and say yours was 90%, the mean oxygen level in the country was 98%, that means that you are amongst rare of the rarest of the individuals, because most 99% of the people would have oxygen level in their blood ranging from 95 to 100%. That means you should immediately consult a doctor. So this is what standard deviation does to the data. It provides a bit more of context. It provides a bit more of visibility of what we are looking into and how that's relevant to us in a specific context. Now moving on to chapter 3, here we are going to see how statistics can be used to deceive and make false representations. First of one is the difference between accuracy and precision. Now both of these terms are interchangeably used, but there's a huge difference between both of them. Now, precision is how specific is your measurement. That is, someone saying a statement like the weight of a lion is around 200 kgs is less precise than someone saying the weight of a lion is 201.5 kgs. That's a more precise statement. However, accuracy is how close you are to the actual target. That is, say in this case the weight of a lion was say actually 150 kgs, then both of these measurements, that is 201.5 and 200, are inaccurate. And that is the difference between accuracy and precision, which is very aptly described in these 4 diagrams. Now it will be very interesting to look at some of the paradoxes. Say, in a popular political debate, a candidate says, our schools are getting worse. 60% of our students had lower scores than last year. And the other candidate says, our schools are getting better. 80% of our students had higher test scores than last year. And let's say as a disclaimer, both of these statements are true. Then that's a paradox. How can that be the case? But it can be the case if the population density of students were very different across all these schools. Say there were 10 schools and 4 schools out of those 10 housed 80% of these students, and these were the 4 schools where the scores had increased, then it will validate both these statements. And that is how we should be very careful in the real world, how we interpret these states and facts. Looking at some other paradoxes, say the government announced that they're going to do tax cuts, and these tax cuts are going to save on an average $1,000 for every citizen. Now, does that mean that every citizen is going to save $1,000 in their taxes? No. When the US administration announced this in early 2000s, the actual median saving in taxes was only $100. That is, 50% of the citizens were saving equal to or less than $100. But why the average was $1,000 then? Because there would have been a lot of wealthy individuals who would have saved way more than $1,000, which would have pushed the average to $1,000. Last but not the least, say there was a TV commercial going on between two telecommunication services giants, one of them saying, "You should join us, we cover 90% of India." Other saying, "You should join us, we cover 90% of Indians." Now, the fact is, both of them are saying the truth. Because one covers 90% of India as a landmass, and other covers 90% of India as population. Hence, looking at these paradoxes, we should be careful and use our judgment to get not fooled by the misrepresentation of facts. Now, moving on to chapter 4, it covers correlation, which is a very important topic because in this world, a lot of variables are dependent on each other, either directly, indirectly, have relationship within them, and correlation is a statistical tool used to actually validate these relationships. For instance, the height and weight are positively correlated, which means as height increases, weight also increases. So generally, a person with higher height tend to have a greater weight. Or study time and exam grades are positively correlated. The more you study, the higher the grades you're going to get. And these measures are generally done by something called as a correlation coefficient. For example, in the height and weight case, the correlation coefficient is 1, around 1, 0.91, which indicates a very strong positive relationship. In the example of study time and grades, the correlation coefficient is 0.67, which is also a very strong correlation between these two individual variables. Now, the mathematical way to calculate correlation looks something like this, but fear not, what we are actually doing here is we are taking the normal distribution graph of two variables, in this instance, say study time and grades, and we are looking what is the directional movement in other graph with respect to the change in direction in first graph. For instance, in let's say study time graph, we are moving from point A to B. Then at the same instance, what and how the grade graph is moving and in what direction. For instance, if by moving study time from A to B, the grades are moving from A dash to B dash, then there's a positive directional movement in grades with a positive directional movement in study time, which indicates the positive correlation. And the strength of that correlation is the movement in the other graph, that is the length of movement in the other graph. Now, small disclaimer though, correlation does not equal causation. Because say there was a movement in a variable due to movement in other variable, that variable cannot be held accountable for triggering that change. Take an example. The number of pirates in seas are decreasing as the global temperatures are rising. So there's a negative correlation between those two. But does that mean the pirates were causing the cooling of temperature? No, that is not the fact. So we have to be mindful of this as well. But this is correlation in a nutshell. The next chapter introduces us to probably the most well-known concepts in probability and statistics, like the density functions, the Bayes theorem, and the Monty-Hall problem. I'll start directly with the case. In 1980s, there was a very popular commercial by Schulz Beer Company where 100 participants were pitched to select between their favorite beer and Schulz Beer, but on a blindfold. And as the experiment proceeded, 50% of the people chose Schulz Beer over their favorite beer. And the commercial went on like this: 50% of the people chose Schulz Beer over their favorite beer, indicating how good Schulz Beer is. Now, this company used probability in a very clever way, because to an ordinary person, the taste of the beer is really indifferential between two types of beer, and hence choosing the beer on a blindfold is a random event with a near 50-50% chance. That means if enough number of people were collected and this experiment was done, then there was a very rare chance that most, a lot, or all the people would choose one type of beer or the other. The outcome would have been 50-50. It's like doing a coin toss. That is, say if you tossed a coin 100 times, then it would be very, very rare that either a head or a tail comes out 90% times out of 100, or 80% even for that matter. Mostly you'll see the results like 60 head, 40 tails, 45 head, 55 tails. And this is what we call the probability density function. If you look at these two diagrams, a coin toss experiment was conducted 10,000 times, where each coin was tossed 100 times. And in most of these repetitions, 10,000 repetitions, there were very, very few instances where either a head or a tail was coming out to be less than 40 out of 100 as a frequency. And we know this by another name, which is called central limit theorem or law of large numbers. That is, as the number of experiments increase, the expected frequency and the actual frequency are aligning and are converging. That is, when tossing a coin, the expected frequency is 50-50, and the number of experiments, when they increase, the actual observed frequency of heads and tails get very close to 50-50. Now up next are slightly advanced concepts of probability. The first one is the Bayes theorem. Now the Bayes theorem is probably one of the most useful theorem in conditional probability. So we try to find the likelihood of an event given that another event, a related event, had occurred, and that is conditional probability. And this particular question goes on like this. And you might have heard this question from the famous experiment conducted by Kahneman and Tversky, the Nobel Prize winners. And this is the statement of this question. John is a meek and tidy soul. He has a need for order and structure and a passion for detail. Is John more likely to be a librarian or a farmer? Now, when this question was asked to a sample of population, most of them chose that John is more likely to be a librarian. However, this is incorrect, because to answer this question, we need few more details. Say, in this particular village, there were 1,000 people, and 950 of them were farmers, and only 50 of them were librarians. And say there were 100 people out of this 1,000 population, sample population, who fit into this particular description type of personality. Then in that case, even if all the librarians were of this particular personality type, that still gives a room of other 50 people being farmers and being of this particular personality type. That means in a population of 1,000, if you pick a random person, there's a 50% chance. That is, he is meek and tidy, and he can either be a farmer or a librarian. That's a 50% chance. And that is Bayes' theorem for you. It basically helps us understand the likelihood of an event given that another event has happened. We'll come to the mathematical details of this particular formula in some time, but this is the summary of Bayes' theorem. Now the next is the Monty Hall problem. Now there's a little historical context behind this problem, but the statement goes in like this. Say you are a participant in a game show host, and you have to choose between 3 doors. One of them has a car behind it, 2 of them has goats. And if you are able to correctly guess the door that has a jackpot, that is the car, you would be able to keep that. So say you go ahead and choose, say, door number 1. Now once you do that selection, the game show host will reveal another door that is not chosen by you, and that is a goat. That means, say he reveals door number 3, behind which there lies a goat. And then he offers you a choice. And the choice is, he offers you a chance to switch the doors. That is, now, while the game show host has revealed that there's a goat behind gate number 3, and you have your current selection is gate number 1, he offers you that you can either stay with gate number 1 or you can switch to gate number 2. And the crucial question is, should you switch to gate number 2? That's the question. And the answer is, you should switch. Because objectively, if you switch, you double your chances of winning the car. That's absurd. Shouldn't there be a 50-50% chance of the car being in any of the doors? So let's scale this problem up and say there were a million doors instead of three. And you went through the same process. You chose door number one. The game show host revealed all the other doors which had goats, rest one, and then he offers you a chance to switch the doors. Now, in this case, you would have chosen a wrong door 99.9% of the time because there were a million doors. And by choosing a wrong door, you are forcing your game show host to reveal all the other doors which had goats, and the remaining door would always be having a car behind it. So the trick is you just have to choose the wrong door in the first place. That is, in the previous case, there was a 33% chance that in the first instance you would have chosen a gate which had car behind it. That means when you make that switch, you increase your chances from 33 to 66%. That means the trick is to choose the wrong door in the first instance, because by doing that, you'll force the host to reveal all the doors which had goats, and the remaining door will always have a car behind it. So I think this is chapter 5 and 5.5 for you. We'll cover the next chapter in the upcoming video. Thanks for joining us. Thanks for tuning in. See you all next time. Bye-bye.